Hello and welcome to this video on representing complex numbers in exponential form. So in our previous videos we have often represented complex numbers in two different ways, either using rectangular form where we have a real component and an imaginary component represented by the letter J, and polar form where we have a complex number represented by a modulus at a given angle theta. But there's a third way to represent complex numbers that we've not touched on so much, and that is exponential form. And exponential form looks like this. So here we see that we still have our modulus r, but it's multiplied by e to the power of j theta. So we can think of exponential form as almost being like a hybrid between rectangular and polar form, because exponential form still uses the modulus r and the angle theta that we saw in polar form, but it also uses this imaginary term j that we saw in rectangular form. One last thing to bear in mind is that previously when we've handled angles such as theta, we can deal with angles in terms of degrees or in terms of radians. But when we're dealing with exponential form, our angle theta has to be in radians. So we're going to see some examples, first of all, of converting between exponential form and rectangular form. But then we're going to see how exponential form is useful, particularly when it comes to calculating the logarithms of complex numbers, which is a bit more difficult to do in these other forms, but it's very easy to do with exponential form. Let's suppose we have this question here where we're asked to convert this complex number 2 plus j3 to exponential form. And you can see that our complex number is in rectangular form. And the easiest way to do this is first of all to convert to polar form and then to convert polar form to exponential form. So if you've been following our videos, I'm sure you're all aware of how to convert a rectangular form complex number into polar form, but if not, then we see something like this. If you're not sure where these have come from, then we do have previous videos on converting between polar and rectangular form. But here we can see that the modulus r is given by the square root of 2 squared plus 3 squared, and that gives us root 13, or as a decimal, 3.61. And our angle, tan to the minus 1 of 3 over 2, well, using a scientific calculator, if it's set to degrees, we're going to get 56.31 degrees. So we can represent our complex number here as 3.61 at an angle of 56.31 degrees. So that's in polar form. Now we were asked to convert to exponential form. Let's just rewrite just to the side here the form of our exponential form here, re to the j theta. Now we've already calculated the modulus r, 3.61, and that same 3.61 in polar form we can also use in exponential form. But remember, we said that theta should be in radians when it's in exponential form. Here we've calculated our angle in degrees. Now we could have just changed our calculator settings to radians to calculate in radians, but if we haven't done so, or if we're given a number in degrees, for instance, then we just simply need to do the conversion where radians is equal to degrees multiplied by pi over 180. But if that's the case, then we can make our conversion here to say that in radians, our polar form would have been 3.61 at an angle of 0.983 radians. And so finally, entering that into the form that we see to the left there, our exponential form, we'll have 3.61 e to the power of j 0.983. Let's try the reverse process now. So here we're asked to convert a number in exponential form, 6.5 e to the power j 1.2, and we're asked to convert that into rectangular form. And again, it's easier to do that using polar form as a kind of a middle step. So converting to polar form, we can leave our angle in radians, but we see that theta here is 1.2 radians. Let's do the reverse process and convert that back to degrees, because what we'll see is that 1.2 multiplied by, this time, 180 over pi to convert from radians to degrees gives us 68.75 degrees. And so in polar form, in degrees, in terms of degrees, our modulus r stays the same, and our angle we've converted to degrees here. So we can say that, I'll just make a note here, in polar form, we have 6.5 at an angle of 68.75 degrees. Okay, so then converting from polar to rectangular form, we've already seen several videos where we cover the conversion between polar and rectangular, but just to serve as a bit of a recap, we see something like this. We have r cos theta plus j sine theta. And expanding that out, we have r cos theta plus j r sine theta, if we multiply both those terms by r. And simply substituting our values for r and theta, we should get something that looks like this. We'll get 2.36 plus j 6.06. And so there we've converted our exponential term into rectangular form. Let's look at just one more similar example of conversion where we are now asked to convert this exponential term, 5e to the power 1 plus j pi over 2, and we're again asked to convert that to rectangular form. Now, the form of this raised power here, 1 plus j pi over 2, can throw people off and seem a little bit confusing, but we just need to remember one of the laws of indices, and I'll just make a note to the right hand side here. If we remember that x to the power of a plus b is the same as x to the a times x to the b, then what we can do is we can apply something similar to our exponential term here. So rather than saying 5e to the power 1 plus j pi over 2, we can break that down and we can say that that's the same as 5e to the 1, I'll put that in brackets, multiplied by e to the power j pi over 2. Now this e to the 1, remember that e is just a constant, and e to the 1 is equal to e. And so really we can evaluate 5e, or 5e to the 1, as just a constant. And 5e to the 1 comes out as 13.59. So we have 13.59 e to the j pi over 2. So here, pi over 2 is our value for theta in radians, and pi over 2 radians is the same as 90 degrees. And so what we could say in polar form is 13.59 at an angle of 90 degrees. So that's our polar form. And similarly, using the same expansion as previously, r cos theta plus j sine theta, we can find our value in rectangular form. And what we'll find is that the cos term evaluates to 0, and so we have 0 plus j 13.59, or we can lose that 0 term altogether. So we've now seen a few examples of converting between exponential form and rectangular form and back again. But in this last little section of this video, we're going to see where exponential form becomes particularly useful in finding the logarithms of complex numbers, in particular the natural logarithm of a complex number. Because the natural logarithm, usually written as ln, is kind of like the opposite process of the exponential. And so what we find is we can cancel out the exponential, as it were, by using the natural logarithm. We'll see a couple of examples. But before we start, I want to remind ourselves of one of the laws of logarithms that you've hopefully come across before. But it's to say that the logarithm, I'll just write that as ln, the logarithm of ab, or a times b, is equal to the logarithm of a plus the logarithm of b. And we're going to use this law of logarithms in our formulation of exponential form. So let's rewrite that again. Let's say we have a complex number z that is equal to r e to the power of j theta, just like we saw before. Well, what we can say is, let's suppose we take a logarithm of both sides here. So we want to find the natural logarithm ln of this complex number z. And so we take ln of both sides. So we've got ln r e to the j theta. So using the law of logarithms that we saw above, we can expand this right-hand side here. And rather than saying that we have log re to the j theta, we can say that that's equal to the natural log of r plus the natural log of e to the j theta. Now what we find is that these two terms here, the natural logarithm, I should say, and the exponential, we can kind of think of these as opposite processes. And so what we find is that these two cancel one another out. And so we have, as a result of that, the natural logarithm of r plus j theta. Let's put this into practice now with an actual example. So let's say that we have a complex number here, z equals 3e to the power j 1.5, and we're asked to find the natural logarithm of that complex number. So using the same method that we saw previously, we can say that if we want to find out the natural logarithm of 3e to the j 1.5, then we can expand that to say that that's the same as log 3 plus the natural logarithm of e to the j 1.5. And what we find is that the natural logarithm of 3 evaluates as roughly 1.099. And we're left here with the natural logarithm of the exponential of j 1.5, and that just becomes j 1.5. And so there we found the natural logarithm of that complex number in rectangular form, and then we could convert that easily enough to polar or exponential forms if required. So here's one last example using some of the same principles that we've seen up till now, and we're asked this time to find the natural logarithm of this term here, 2e to the power 1 minus j 0.8. And so if we write that out, we'll say that the natural logarithm of our complex number z is equal to the natural logarithm ln of 2e to the power 1 minus j 0.8, which, expanding in the same manner, that's the same as the natural logarithm of 2 plus the natural logarithm of e to the power 1 minus j 0.8. And again, this natural logarithm and this exponential can cancel one another in a sense, and we're left with ln2, which evaluates roughly as 0.693. So we have 0.693 for that ln2 term. Plus, well, that natural logarithm and exponential are both gone to leave 1 minus j 0.8. And we have two real terms here. We have the 0.693 plus an additional 1. And so our final result in rectangular form is 1.693 minus j 0.8. So I hope you found this video useful, first as an introduction to exponential form and converting to and from exponential form. But then the key point here is the usefulness of exponential form for evaluating the natural logarithm of complex numbers.